initial comments on the deliverable. Okay, so articulating what has been a long set of code into pieces allows us to identify dependencies between those pieces. What depends on what? The interactions between them. And part of it is that they have a separation of concerns. Those pieces are not willy-nilly pieces that are, just random subsets of code. They're logical chunks that have some meaning to them. They have some function in life that they accomplish, and hopefully each of them has its own sort of defined role that's semantically meaningful. It does something. It loads the input file in, or it writes the output file out, or it goes through and applies a transformation to things in this space. So each of those pieces into which you break it should have a meaning associated with it, a goal associated with it, a role that it takes on. Why is it that by breaking into pieces, the interactions are more obvious? What depends on what? I'd say that if we break into pieces, those dependencies are clearer. Why?
Because you can see what calls what.
You can see what calls what, and you can see when it calls it, on what does it depend. So if you look at the code, and it's all one big hairy mass, which it is right now, it'll be hard to look at it and kind of see, there's all these variables here, variables there, there's all this code, what kind of uses what? What is this depending on? What is that? Where is this variable used? Where is it not used? Is it only used in this little loop? These are things we spend time trying to chase down visually. Where if we break it up into pieces, often a lot of those variables just live in a little piece, right? This variable only lives within inside this particular function. Outside, you don't have to worry about it at all. And whatever that code depends on, it's clear because it's in a parameter passed to that code. It's really clear what this depends on, and it's clear what this returns, what the end result of this is. Now, I'm simplifying things, of course. What am I simplifying? What am I leaving out of the equation? Talking just about return values and parameters.
Global variables and global state.
Yeah, global variables and global state, ladies and gentlemen. Our code, ladies and gentlemen, may in fact engage in a process known as side effecting. Okay, by side effecting, what I mean is that it changes state of the system. It modifies things that lie outside of itself and that persist outside of itself. Okay, so it modifies the data structure. Yeah, modifies contents of the screen. Modifies, what's stored on disk or whatever. It has a side effect that persists beyond that code, right? Have you folks heard in your other courses? Have you heard about? Has that term been used? Side effects? Yeah. Okay. Where did you hear about it? Was it in 215 or 214 or 340? 340. Okay. Yeah. Yes. So Dr. Duchin and I have a lot of shared aesthetics, but our personal habits are a little bit different. I'm told that one of the most notable ways in which we differ is that I tend to wander around. My colleagues in Australia talk about me needing a bear pit. I sort of wander around and gesticulate and kind of exhibit ursine characteristics. Dr. Duchin, I know he has a very interesting didactic style where he'll talk in one place and he'll speak from that one place, and then in a moment of great significance, he will move one step to the right or one step to the left, and that will emphasize a very important point. I lack that consistency. I wander like a peripatetic Bruin. I also probably speak a little bit differently than him. In any case, the point is that he and I share a lot of our perspective on software, and this is one area with side effects you'll find us both using. It's a term that you'll find in certain sub areas of CS. I'm glad you've heard it. So side effecting messes the situation or complicates the situation from what I described. But at a general level, a lot of things a function will depend on, and a lot that it changes will be in return values, or will be in parameters and return values respectively. So at least you can carve off a lot of its dependencies right there. Does that make sense? It's very clear what we're passing it. What does it need to do its job? And if we're just looking at hairballs of code, it's not clear visually what this is depending on, what it uses to do its job, what its end result is, because it's all tangled. It's all tangled together. Okay, so these are some good comments, and I'd like now to talk about how these apply. So if someone could get the light back at the door there and try to turn off the light in the front. I'm going to run through some slides. My slides in this course, thanks. Do people want one of the lights on?
Yes, please.
Well, okay. Could maybe you put on the light more towards the back? I apologize. We'll frob the lights once, and then we'll understand the code for them. Okay. So is this better?
Yes.
Okay. Again, I've really got to get on to the tech staff with this, but we'll in ITS we'll go with this. Okay. So we talked last time about the challenge of complexity. Software is complex. And one of the things that almost makes up a complex system, as folks who have taken 394 will recognize, is you have a system where there are pieces and interconnections between them. And it's more than about the pieces. Interconnections are extremely important because it leads to surprising behavior. It leads the system to exhibit behavior as a whole that's very different than the behavior of those pieces. And the interconnections make that possible. And software is very much like that. Software has a unity to it that goes beyond the individual pieces. It's about how they come together. And we talked about how modularity last time. This is just a review. How modularity lets us try to manage this complexity by making attempts to decouple the pieces of the system, to articulate separation of concerns. Pieces whose job in life is clear, whose dependencies in life are clear, and having a well-defined set of interfaces between them. Contracts by which one part depends on others, okay? So we talked about separation of concerns. And last time we talked about some separations of concerns. This part of our program deals with persistence to the database. This other part with network connectivity and connecting to the server and communicating via JSON. Yet this other part of our program is responsible for the graphical interface, and this other part for the user input, processing of the user input. We talk about things like model view controllers or three-tier architectures from the web, and these all adhere to these sort of nice separations of concerns. And what that means is you know where to go to fix what sort of issue, and you can swap out the pieces. So if you want your system to be tested, you put in a mock for the interface to the server, and now you can test this thing without actually depending on network connectivity. You can pretend you're dealing with a server and see how your code responds to server error conditions, etc. So modularity is the key to building systems that are testable, reliable, and buildable by teams that can be reviewed and modified and evolved, etc. And it really is a divide and conquer technique. It's not to say it's easy. It's often really hard. The units into which we divide our code will depend a lot on what we're trying to accomplish, the performance needs, etc. But fundamentally, this is the technique we use. Okay, so modularity, a good thing and one that will be following us throughout the term, whether it's aspect-oriented modularity or functional or class-based or what have you. And I said abstraction is the key to modularity. building up pieces that handle a number of different cases, hide the details between those cases, and they allow us to handle with a certain generality a set of cases. So they abstract over certain details. So I argued we had a square root function, right? And instead of having a precise square root function and an imprecise, we have one square root function that can take an argument that indicates the tolerance, the precision with which we wish to calculate it. And we can call that with a larger degree of tolerance or smaller to use either a more precise or less precise. Okay. And in this class, we'll talk about a bunch of types of abstraction. Today, we're going to be talking about that first, functional abstraction. And this is going to follow us for the next bunch of lectures in more sophisticated ways over time. Okay. So here, we're going to be talking about the use of functions to characterize these kind of units of functionality, of sort of work to be done. Okay, here we're going to be building pieces that do some work while hiding details on exactly how it's done. The particular algorithm they use internally, the particular data structure, or whether or not they use a cache internally, that's hidden within the function. Right? So methods here are functions. Methods are functions on objects that, have additional access to that object state, but we could think of them as a type of function. They might compute a value, for example, hide the algorithm by which they compute it. They might test some condition, some logical condition that we're testing. When you're dealing with that code for Thursday, think about when you see a condition in there, if something, what is that condition testing? What's the meaning of that condition? And see if you can abstract it into a function. See if you can abstract it into a logical thing that returns a Boolean if this is true. And by so doing, you're capturing the underlying meaning, the intention behind that condition in a way that might be important. Often that will clean up your code a lot, because a lot of expressions you see again and again and again in if statements or while statements or conditions on filtering or whatever will suddenly just use this abstraction. Like they'll ask, is this out of bounds? Or is this in bounds? And that's a meaningful thing, and you can hide the details of how that's computed. So when you look at the code, it's much clearer, because you don't. Ladies and gentlemen, we have hard enough life as software engineers. We have enough inherent complexity to deal with day to day. We don't need gratuitous complexity. We have enough challenges to deal with. We don't want to have to face unnecessarily crufty code that we have to figure out, spend a lot of time figuring out. If you can hide the details in functions, you simplify people's thinking a lot, because they only need to check out the function with the details if they need it. And a lot of the time they just look, oh, okay, you're testing if it's in bounds. Fine. I basically understand what that's doing in a much clearer way than if I look at some long predicate. Is this less than that? Is it, is x greater than or equal to 0? And is it less than this? And is y greater than or equal to 0? Is it less than this bound? And if I see that, it's a lot of cruft, and it's not clear what it's doing, and it just introduces uncertainty. If it's a nicely named function, is in bounds, it's clear. If I need to see it, I can go do so. If I am not interested in that part of the code, particularly other than to know what it's basically doing, I never have to go look at that function. Does that make sense? Okay, functions hide details, because why add gratuitous complexity when our lives are already so complex, right? Okay, so functions might compute a value, test a condition. It's one of the big things I look for in my students' code. Perform some action to update something, right? Update some data structure, and maybe return a representation of some information or what have you. Let's talk about encapsulation. So abstraction, capturing these units of functionality, hopefully with a separation of concerns. They each accomplish something there should be an encapsulation there. There should be this hiding of detail, where the details of how it accomplishes it is hidden. Now, it can't. It needs to provide some promises to the world. If there are clients, if there are things that are going to use this function, things that are going to use this class, whatever level of abstraction we're talking about, let's deal with functions here. There's things that are going to be counting on its return values, counting on what it needs to do its job and what it returns, right? Or other aspects of what it modifies in the state, what it changes, right? What properties does it ensure? Does this function send a message out over the network? Does it update the screen? These are things you might want to know, right? So a function can hide its internal details, but it's got to make some promises for anyone to have trust in using it, right? It's kind of like if you were running a company, ladies and gentlemen. If you were running a company and someone was interested in contracting you from software, you have to make certain promises of what you'll accomplish, and deliver, and how soon, the budget, the time, etc. But you want to retain some guarantees that you can modify the details. So if you need to hire someone part-time, or you need to bring someone on board full-time, or you need to change the details of your software development environment, you want the flexibility to do that, right? So there, when you're running a firm, just like when you're writing a function, you want to be able to separate what you promise to others from what you can change internally. So you want to hide details from outside. That gives you the flexibility to change them. And you want to promise certain things to others that won't be changing. You want to have a contract. So when you go ship a package with FedEx, you have a contract with FedEx. They promise you certain things, right? I want to get this package to Toronto by noon tomorrow. And they say, as long as you deliver it to our FedEx office here in Saskatoon by noon today, it'll get to Toronto by noon. That's something that they've guaranteed. There's a lot of things that they don't guarantee. They don't say whether it's going to get to Toronto via a supersonic jet or going to ride on the Blue Flame. They don't say whether it'll be attached to a dog sled. As long as it gets there, that's their business. As long as they can adhere to their promise. So in contracts in life, just like as in contracts in our software, we have certain things we hide, certain details that we don't expose and that we want to be able to change, and certain things we promise the world. And the way we do that is we separate out the interface from the implementation. So we talk about, there's an implementation, which is all the details. The implementation is up to me as the abstraction creator. I'm giving you an interface. I'm giving you a contract that allows for me to change my implementation, right? To modify my implementations over time. And this facilitates modularity. It's a separation of concerns. I take care of my business, and I give you these guarantees. You match what I need from you, and I'll guarantee that you'll get some value from it, right? So, as we'll see, specifications will be key for doing this. We're going to wrap things up in pieces, but to prevent that from being chaotic, we need a certain amount of guarantees between these pieces. After all, a system, a complex system, is more than the sum of the pieces. It has dependencies between those pieces, and to address those dependencies, we use an interface. And the way we describe an interface is with a specification. We provide a contract. The specification says, you give me this, I need this to do my job, and I'll give you that as a result. You give me the values of these parameters, or a data structure, global data structure that matches these things, and I will guarantee these conditions back. Okay? So this separation of concerns, supported by providing separation of interfaces from implementation, where each component is can handle its own little part of the world, its own little reasoning, is one of the key strategies we use. And it's a key strategy I'll be looking for putting into place in the next few weeks here. This allows us to modify our code, and it allows us to be concerned predominantly with things going on in each piece separately when we're creating that. Okay? Okay. So why use functional abstraction? Well, a number of points here. Easier modifiability. One place to update things. We have different pieces, each have their job in life. There's the piece associated with checking if it's in bounds. There's a piece associated with loading the file in from loading a file into memory. There's a piece associated with writing it out. There's a piece associated with stepping the system through one step. Each of them has a role, and we know where to go to change it. They're not scattered all over. Okay? Transparency. What the code does is clear. We have recurrent reuse of this condition. Is it in bounds? Instead of hard coding that in many, many places, we have a very nicely named function call, and it's clear what it depends on. Okay? It's easier to reuse, so we might have another program which can reuse pieces of it, like loading the file in or what have you. Reduce complexity. It's clear what the code does, and therefore it's less likely you'll make mistakes. You're not repeating the same condition again and again and potentially making a mistake each time, replacing a greater than or equal to 0 with a greater than 0 one time. It's easier to test. Why is it easier to test if we have these things broken up into pieces? You test the pieces.
You can test them without calling all the other stuff.
You could test them without calling all the other things in the program. They're more or less independent. Yes, Warren.
Another thing is if you work on each piece individually, you can test it without having any knowledge about any of the other pieces.
That's right. So you can hand it off to a tester. They don't need to know all about the program. It has a well-defined contract, right? Give me this, I will give you that. In fact, this is so fundamental to testability that, people have argued that we should be able to do automated testing down the road. As our specifications become more precise, we should be able to allow software testing systems to basically read these specifications and automatically generate test cases from them. Test, okay, so it requires this for these variables, for these parameters, and it guarantees this. We can feed it things that match its conditions and see if it returns, observes the post conditions, right? It's really fundamental stuff, but it's fundamental stuff for making progress in automated testing. But for day-to-day stuff, it makes a lot of sense. If it's human testers or automated testers, the point is there's much greater clarity if you see what's promised. If you don't know what's promised, if you don't know what this does, what its job is, it's hard to test it, right? If it's all in one hairball, it's hard to test it. To test one thing, you got to test everything. That's not going to be very good either. You want to divide it up into these pieces, each of which will have clear job in life, clear function, clear guarantees, clear contract that allows you to test it well. Do people understand that point? What's another mode of testing, though, that doesn't involve just, let's put it this way. Suppose we do have pieces that call each other. We're going to, right? We're going to have pieces that call each other. How do we test each individually if it calls the other? So we have A and it calls B, C, and D. How can we test A without B, C, and D?
Mocking.
Mocking, indeed. Mocking, or it's variants like faking and stubs. So stubs is an older term. When I was a young person, I think the Earth was still cooling then, and we were knocking on rocks and so on. When I was a young person, stubbing was sort of the term of art. And in large software projects, we would stub out code routinely So we would have a stub version of this code. We would test, the other functions with this stub version, and then we would, when appropriate, substitute in the full version, or could put the stub back for further testing. Fakes are another level of sort of adaptation of that for object-oriented programming with very simple functionality. What's the difference between a fake and a mock? Anyone? Well, give me an example of a stub. We're dealing with functional abstraction. Give me an example of a stub. So suppose that we had a function that was looping through and it was calling things to ask, is this in bounds? What would a stub potentially be?
Always returning true.
Always return true, or always return false, or return something based on a very crude condition. So maybe you're dealing, is it within bounds in a circle, and it just used a very crude condition, which is a square within that circle or something like that. The full logic hasn't been developed yet, maybe, or maybe it has been developed, and we just want to see how it behaves under true and false conditions at times. So with stubbing, often it's extremely simple logic, like you return a simple value, or you have a simplified version of the algorithm that doesn't handle certain cases. So stubbing is often dealing with very, very simple cases. In some cases, the stub actually may be more sophisticated, and there we really get into the realm of sort of stubs which are used on an ongoing basis to test algorithms that are quite central. So maybe we have a stub, for example, which uses an exhaustive search compared to a really clever heuristic search. And we want to be able to substitute it in, even though it would be prohibitive in user code, and actually see if the quality of our search results really markedly increase. Okay? So it may not be just to find errors, it may be to find other types of deficiency in our code. Or we may want to compare. Maybe we have a really clever algorithm we think should always be able to find the correct answer, and we compare it with a brute force exhaustive one. And we see, do they give the same results and identify the correct results. We give it kind of an obvious algorithm that's very expensive versus an unobvious one. And we only use this stuff during testing, but it's not trying to find errors per se. But the point is, the bigger point here is the only reason we could do this is because the code is broken into these chunks. So we could take a chunk and substitute in another one. Fakes. Fakes are often used in an object-oriented context. With a fake, you're also dealing with simpler functionality, simpler sorts of logic. So definitions of these are not hard and fast, but that term started to be used more in the object-oriented context. So you have a fake version of an object that is very simple, and it's kind of stub-like in the sense it's returning values. Mocks will do more than that typically, and if you use JMock or Mockito or these frameworks, which I would encourage you to do, they allow you to more sophisticated things. What might they allow you to do?
See how many times it's called.
Guarantee that it's only called once. Guarantee that this parameter is greater than that one. So it's actually got some logic associated with it. And the beauty of a lot of mocking is for important cases, not all, but important cases, you can actually declare, I want a mock of this component, and it will actually build it for you, and it will test conditions that you specify declaratively. You don't have to write the code to do it. You say, test these conditions. Ensure that this thing passed is never null. Make sure that this parameter is greater than this other one. And it will actually create that for you. So mocking has come a long way since the early days of stubbing. But the basic principle is the same. By breaking up your code into pieces that are well defined, you have these boundaries, these interfaces, which are separate from implementation, and therefore you can substitute in a new implementation it returns a simple value. It looks a value up in a database and returns it. It returns a random number, depending on your needs. And you can substitute that in. Does that make sense? Having these pieces in functions, and down the road we'll see with classes, allows us to do that. And then peer review. If you have to review the whole 9 yards, if you have to review the whole hairball together, you've got a more difficult challenge in performing peer review, right? Okay. Side effects. I talked about side effects. Side effects are something that are important to reason about, important to manage, important to tame. Side effects complicate our reasoning. When we have a function, it's a nice situation if its job in life can be fully characterized in terms of preconditions, postconditions specified for parameters and for the return value. If we start to have it read things externally that are separate from those, or write things, change things, it gets more complex. Why does it get more complex?
You can't see them in the returns.
Exactly. You can't see them. You can't see what it changed. So that's an important thing. Or you can't see what it depends on, right? Why else is it tricky?
Because you might logically think that an error comes from one place, but it might come from a function that didn't describe that. You might modify other things.
Exactly. Yeah. So there you might be attributing this change to this update to this variable occurring in this place. It's the only obvious update you see, but it's occurring in this call to a function earlier that magically mutates that variable through a pointer to some data structure or what have you. That's really, that can get kind of hairy. You can't really see. There's kind of this ghostly updates occurring when you're calling off to the functions. What you see is not what's the full context of what's going on. If everything depends just on the values passed as parameters and the values returned, the dependencies are clear, are they not? What depends on what? You can see very, very clearly. But if it's depending on global data structures, those dependencies are not clear. There's kind of this ghostly thing going on behind the scenes that you can't see but is modifying things, right? So there's many things hidden in this kind of welter of detail often. If you have that code without any functions at all, it's particularly confusing. Let's talk about this. Okay, so here we see some code. This is what I'd call sort of moderate. It's not actually too crufty a code. It's not horrible. At least we have decent names. Total revenue, right? Here we have total revenue equals 0, and then we have some loop, and we're computing total revenue. We're adding it up for each city. We're adding in the revenue from that city, and then we're creating some sort of array, which is the fraction of the revenue came from a given city. So we're taking the total from the city and we're dividing it by the total revenue, and the revenue here is a double. Okay, so there's some code, not terribly bad. But what's missing here? What's missing? There's some code. What can we do to clean this up? What can we do to clean this up? Yeah.
You could probably just make a function to return total revenue.
Yeah, okay. We could wrap the whole thing up in, we could wrap this first part up in a function, right? First part up in a function to return total revenue. Okay, good. What's another thing we could do? Well, I would argue there's some hidden structure here. I mean, after all, this is just totaling this up, right? This is summing up this. And this is basically normalizing this array. We're taking each element of the array, we're dividing it by a constant. Those are pretty commonly needed types of operations. And so, we could clean those up. What's going on here is when we have this code as a whole, it's not clear what the dependencies are. And this is what makes it a little bit difficult, to understand. This code is far from really, really crafty. If a student gave me this code, I wouldn't leap up from my seat.
Might fall out of it.
Indeed, yes. What's up? No, that should be fine. Yeah. Okay. Thank you. Thanks a bunch. So, ladies and gentlemen, here we have a dependency that is not obvious when you look at the code involving these variables. Do you see this? Total revenue here came from there, and it's coming from there. And when you go to look at code like this, to really debug it, to understand what it's doing, maybe you have to take it over, you've got to kind of trace back these dependencies. Where does this come from? Oh, that comes from there. Where does this guy come from? Oh, he comes from there. And then, this array revenue from city, it's being indexed by this. There's all these dependencies here that are not clear, that are not immediately clear when you glance at it, but which can be traced. Do you see what I mean here? We're tracing kind of what depends on what, because if we want to change a variable, we want to go see where it needs to be, change variable name, we need to see where it needs to be changed, we want to change the logic. Okay, so here, ladies and gentlemen, here we have another case. So this is a bunch of code. So here we have a dot product. This dot product, here we're basically summing up the elements multiplied by each other. Why is that? What is that called in linear algebra? It's called the dot product. Thank you. Sorry, I should have made it obvious. I was asking. I just want to make sure I know you know what dot product means, right? The dot product. Okay. Here I'm taking the magnitude square of those same variables. I'm summing up for x, the square of the elements of x, right? And here then I am taking the square root of that magnitude. So I'm taking the magnitude, and I am allocating an array, and I am basically taking a value of this of each value of x, and I'm multiplying it by the dot product divided by the magnitude. What's going on here conceptually? Can anyone tell me? What's going on here?
Are you creating each vector into its unit? I'm not sure about the terminologies anymore.
Okay. Yeah. Yep. You're onto something. Unitizing a vector. So we're actually here performing linear algebra operations at a high level that indeed involve, here you're normalizing by magnitude, here you're taking this dot product, in fact, is what we're doing is we're rescaling it by the cosine of the difference among these vectors. Let's go see what makes this code complex. What makes it complex to understand is often, again, we've got to trace back these dependencies. Do you see that? There's a higher level structure here, I'd say, that's hidden. Similarly, if we have code like this, we have a lot going on. So here we have pointers. Here we have complex expressions, and we'd like to be able to simplify this code, but we're trying to reason through, okay, this is K here, and this is K here, we've got K there. This is horrible code. That code is the type of code up with which I will not put, much as Winston Churchill said that about that English. Okay. So, we've got limited time here. So how do we deal with these things? Well, one of the big ways in which we deal with these updates and changes to side effects is encapsulation. We put it into into code, right? So, a better alternative is to take this code here, and break it up into, a set of pieces that have clear names associated with them. So the first of these here, this revenue fraction for city, the first of the examples we looked at, we took the revenue fraction for the city and we computed it by an operation called normalize array. That's really what's going on here, ladies and gentlemen. We're normalizing the array associated with the revenue per city by the count of cities here. So this is the revenue fraction for the city. We simply divide it by the count of city here, and actually, excuse me, I'm reading this off. So we're normalizing this array by the count of cities, and then this array total here, okay, right, this is just the last argument of that. So this is the normalization, this is the count of cities, this is the array that we're normalizing, and this is the total of the revenue across all cities. So this whole thing is summarized by this basic call, which contains two calls, right? One is the array total, that's this piece, and one is the normalization of the array, which depends on the result of that array total, and that's hence this third argument. I apologize, this is over here. I'm not sure, it must have been weirdly wrapped, and that was my bad. Should have caught that. So this should be over here as the third element. Does that make sense? So we have a function whose job in life is to normalize an array. That's a high-level operation, and its arguments are determined by either pre-existing values or the results of another function. The dependencies here are clear. What depends on what? The call to this depends on a value that's computed by the return value of that. All these details about how we're performing this operation are hidden within these calls. Does that make sense? Okay, let's continue to look at this for some example code. So, here the dependencies are clear, right? Here's the sort of declaration of normalized array. You don't have to look at this code unless you want to. You can see an instance of this here. You can see this, this being called. Let me move that over because this is really confusing here. Come on, man. Here we go. It was a new line. Okay. Unfortunately, it's just too short. There we go. And the code that calls this is to a degree self-documenting. I mean, here we have normalized array, here we have array total. This is totaling up this array, then we're normalizing this array by that total. All right? It's fairly documenting. Many places in the code can use these functions, array total, normalize array. Those are high-level operations. And the function can change without needing to worry about changing the code that calls it. Does that make sense? We can also test these functions. Normalize array and array total can be tested. Okay. Here's this dot product. Here we go. So this is high-level summaries. Here we normalize the array, use that same basic method, and we basically normalize it by the magnitude divided by the dot product of this. Once again, these are clear. What these depend on, clear. They depend on their arguments, right? Their parameters. And here we have basically the high-level operations specified. High-level operations are totaling up an array in terms of dividing each element of it by a certain constant, and in terms of things that are meaningful in that domain, like magnitude and dot product. Does that make sense?
So how is tracing back helping us better encapsulate the code?
So the trait, you mean here?
Yeah.
This tracing back is what I'm contrasting with this. This takes a certain amount of cognitive complexity.
Okay.
If you want to go modify this code, you need to do some of this tracing back. If you want to change, for example, the name of one of these variables, you need to check what depends on it elsewhere and modify it, right? If you want to understand how the code works, we often, when we're looking at code, we ask, where did this come from? What computed this? We're using a variable here, and we're trying to figure out where was that computed earlier? Was it computed only in this place or in this other, somewhere else? We spend a lot of time when we have code that is fairly complex. We spend a lot of time tracing what it comes from where. Where did this come from? Where was this computed? Oh, okay, it was computed. This guy was computed up there. Magnitude was computed here. We spend a lot of time tracing it. And my point is that introduces a lot of overhead. It introduces a lot of unnecessary complexity. As I say, we as software engineers have enough complexity, inherent complexity we got to deal with. We don't need the complexity to trace through visually what's going on. When we encapsulate things in functions, we take things in functions, we give them a nice name, they have a clear job in life, we simply call them, it becomes clear on what they depend, it becomes clear what the basic job of the function is, because we can use an intention revealing name, and it becomes clear what the dependencies are. What depends on what? Here, to compute the normalized version of x, we are depending on x, and we're depending on the results of calling magnitude and calling dot product. You could figure that out from up here, that the result computing normalized x depends on the dot product, depends on the magnitude, and depends on some normalization. But it would take a lot more kind of sifting through what's going on. When you have this, it's clear. It's almost like a bit of algebra. You're saying, okay, computation for z depends on x and y in this sort of way. Does that make sense? I want to make sure this overall understanding has been imparted. So when we have lots of code in front of us, the dependencies are not clear. When we encapsulate things in methods, not only do we have greater testability, not only do we have greater ability to evolve that code, but we have the ability to more clearly understand the dependencies for that code, because the dependencies are captured in parameters where possible and return values, and by having, for example, a nested statement like this, we have something akin to an algebraic formula. We have something that depends on a few things that are laid out clearly, which may themselves involve some operations. Does that make sense? See if for Thursday you can take some of that code in the code I gave you, which has got cruft, more so even than this, much more so, and see if you can refactor it so that the dependencies are clear, so that there's a separation of concerns, so that there's testable units, and so that you use intention revealing names. Names that connote what something is accomplishing. You're going to have a hard time for certain things. It's not going to be clear what this does. And that's part of why I'm giving that to you, to see when you inherit crufty code, how challenging that is. And I'll give you a version of the code that's been decrufted. Okay? Okay, that's all for today. Thank you, and I will see you on Thursday. Give me just a second, and I will get this.